Okay, so thank you everyone for coming to our first head seminar of the year and of this semester. It is my pleasure to introduce the first of our speakers, and today is a very exciting day because we have two visitors giving talks. It is my pleasure to introduce Sandra Raimundo, who did her PhD at the Institute of Astronomy at the University of Cambridge in the UK. And this was followed by postdoctoral roles at CISA in Trieste in Italy and at the Niels Bohr Institute in Denmark. She then became a Marie Curie Global Fellow and assistant professor at UCLA and at the Niels Bohr Institute in Denmark. She is now a tenured assistant professor at the University of Southampton in the UK and coordinator of the Southampton-Harvard Student Exchange Program. So Sandra will be here until tomorrow after lunch. So if you want to speak to her, please make sure you approach her at the end of the seminar to let her know. And it's also, I would mention, a nice way of starting the year because probably our last seminar of the the academic year will be the Southampton student seminars. So it's exciting. Okay, but thank you so much, Sandra, for accepting our invitation, and the floor is yours.
Thank you. Thank you very much. It's a pleasure to be here. So again, I hope you had the chance to meet our Southampton students. We'll be here until May. If you want to know more about the program, please come and talk to me or send me an email. So you've probably met Diego Altamirano, who's the past coordinator. We're doing it together this year. From next year on, I'll be the main coordinator. But let me focus on the science. So my talk is about how to feed supermassive black holes, how to make them grow. So we know that supermassive black holes live in the center of galaxies. They have between 1 million to 10 billion times the mass of our sun. And they seem to be ubiquitous. Everywhere we look, every center of galaxy we look at, there's a supermassive black hole in there. One of the most puzzling aspects about this is the difference in size, physical scale. Between the size of a supermassive black hole and the size of the galaxy, there's a difference in 4 orders of magnitude in physical scale. So any relation between the two is puzzling to understand because of the difference in scales. And one of the main correlations that we know about the black holes and their galaxies is this correlation between the mass of the black hole on the y-axis and the galaxy mass. This is a proxy for the mass of the galaxy in the x-axis. And these are observations of galaxies in our local universe. And we see this correlation between these two properties. So it means that there is a connection between the black hole and the galaxy. So somehow either the black hole knows about the size of the galaxy in which it lives, or the galaxy controls how big the black hole can get. And we refer to this as a possible coevolution of the two. The mechanism by which this happens is still not fully understood. One of the possible or best candidates to regulate this coevolution is the active phases of black holes. So this is an artistic impression of a supermassive black hole in the center of a galaxy surrounded by gas. And when black holes are actively accreting gas, they are growing in mass, but they're also this whole process of gas accretion heats up the gas and results in the emission of large amounts of energy into the surrounding medium, and that is the galaxy. So when this happens, we have an active galactic nucleus, because the black holes are in the centers of galaxies. When they become active, we call them AGN for short. And we think that this process of black hole activity, so the energy that is being released, is a potential candidate to regulate this coevolution of black holes and galaxies. But also, it's a way to grow the black hole with material from the galaxy. So we think this could be a key aspect of black hole and galaxy coevolution. So my talk will be focused on this process that we call black hole fueling or black hole feeding. And it's the process by which gas is moved onto the black hole and results in the accretion of gas by the black hole and the increase of its mass. So We know that this happens, that's how black holes grow, but we don't exactly know how does the gas reach the black hole. And like I said before, there's a big difference in size. So how does the gas move from the galaxy all the way to the black hole? It needs to lose angular momentum, but we don't know exactly how this happens, what are the main mechanisms. And we hope that if we understand this process of black hole fueling, we can understand why some black holes are active while others are not. So if we look in the local universe, only 5 to 10% of supermassive black holes are active. We don't understand why not all of them are active. So if we can understand this process, maybe we can also understand this big question. And for this process, we basically need two ingredients, right? If we want to fuel a black hole, first we need to have gas. So a supply of gas needs to be available. And secondly, we need mechanisms to transport the gas. This has to do with the presence of dynamical mechanisms that can facilitate the loss of angular momentum. So this is what we need. So remember what we need for this. So one of the things that we wanted to look at in our research is where can this gas come from? One of the possibilities is from the outside environment of the galaxy. So we know that galaxies interact. This is an image of two galaxies interacting. It's a little bit difficult to see because of the contrast, but there's a tail of gas in between the two. So these interactions can be mergers, can be tidal interactions, flybys, and in some cases we see this transfer of gas from one galaxy to the other. And when we see something like this, we refer to it as external accretion of gas, because one galaxy has gas coming from the outside. So there's fresh supply of gas. And in some cases, because the gas is coming from the outside, we can end up with very interesting configurations. So this is an image of a polar ring galaxy. So you can see here in the x-axis or the horizontal direction, this is the distribution of stars in the galaxy, so the main stellar body of the galaxy. And perpendicular to it, this is the distribution of gas that came from the outside of the galaxy. So this galaxy had an interaction in its past, and because the gas came from the outside, it ended up misaligned with respect to the stars. So in this case, and it's a very beautiful thing to see, we see this 90-degree misalignment between the two. So if we were to measure how the stars and the gas are moving, they would be misaligned by 90 degrees. But you can think of different orientations for the interaction. So we can end up with interactions where the gas and the stars rotate in the same direction, in the same plane, can have misalignment angles all the way to 180. And this is when we have stars and gas in the same plane, but the stars and the gas rotate in opposite directions. So this is called counter-rotation. So we can have all these configurations, but if we see what we call a strongly misaligned, kinematically misaligned galaxy, that's a misalignment angle above 30 to 45 degrees, then this is a very good signature that there was a past external interaction in the history of the galaxy. So we can use these observations to then tell us there was a fresh supply of gas in the past history of the galaxy. So let's put this together with what I've told you in the beginning. So we want black holes to be fueled, and the question that we wanted to ask in our work was, can this gas that is misaligned, can it fuel the black holes in the center of galaxies? So this is what we wanted to test. So to do that, we need, first of all, a very large sample of galaxies, and we need information on how the stars and the gas move. And the best way to get that is through integral field spectroscopy. So this is an observational technique where we can get the velocity at different positions in the image, which makes us able to determine how gas and stars are moving. So one of the products that we obtain are these velocity maps. So here on the left, this is a map of the stellar velocity in the galaxy, and on the right is the map of gas velocity. Blue are motions towards us, red away from us. So you can see that the rotation of the stars and the gas are in opposite direction. So if we measure the angle of rotation and compare it, we get a kinematic angle of around 180 degrees, which means that this galaxy is in counter-rotation. And just to clarify, this is not a local misalignment, so we're looking at the bulk motion of the gas in the galaxy, so large scale. So if we use our data and calculate this misalignment angle for all galaxies, then we have a sample of galaxies for which we know how the stars and the gas are moving. So then our goal is, if we know this stellar to gas misalignment angle, can we then check which one of them or which subsample has the highest fraction of active black holes? So is there a correlation between the two? So we did this for a very large sample of local galaxies. They have to be local because this type of data we cannot get at high redshift, unfortunately. So we do this for low redshift. This is one of our results. I'll show you. In the x-axis, this is the kinematic misalignment angle between the stars and the gas. So on the left side, I'll show you these are galaxies where even if there was an interaction, the stars and the gas ended up aligned. And here on the right side, these are misalignment angles above 45 degrees. So we're fairly sure that there was an interaction and the gas and the stars are misaligned. And here on the y-axis, this is the fraction of AGN, so active black holes. So when we do our analysis, we see that there's a significant difference between galaxies with alignment versus misalignment. And there's a much higher fraction of AGN in the misalignment group. And this is statistically significant, and it hadn't been seen before. So this was the first time that we've shown this with observations. And this tells us there's a connection between the presence of this kinematic misalignment and the promotion or the increase of the fraction of active black holes. And this is important because we're looking for ways to fuel black holes, and this is the first time that this observational result showed that. So you're probably thinking, because I told you that this misalignment comes after an interaction, and we know that galaxy interactions often bring gas. So what is the main driver? Is it just because galaxies had interactions that they have a higher fraction of active black holes? Or is it actually the misalignment that helps promote gas to the black hole? So what we did was to select a subsample of galaxies that had visual signatures of recent interactions. So this was based on the images, they had tidal tails, they were disturbed. So we know that all of them had recent interactions. And then we did the same analysis. So we looked at, within that sample, the ones where the interactions ended up aligned on the left, and the ones where the interactions resulted in a kinematic misalignment. And we see that the fraction is still much higher if the interactions result in a kinematic misalignment. So our conclusion was that the driver for this increase in the fraction of active black holes is due to the kinematic misalignment and not only the interactions themselves. So to try to understand why this is, so first of all, let's start with the morphology. So we know that gas misalignment is relatively common, mainly in early type galaxies. So if we look at early type galaxies that have gas, around 40% of them show this misalignment, so it's relatively common. And the reason why this is for early type galaxies is because they don't have a lot of native gas to start with. So if there's a supply of fresh gas coming from the outside, it can replenish the reservoir and it will dominate the dynamics of the gas. So this mechanism is likely very important for early type galaxies. And I've shown you observational results, but there are numerical simulations that also aligned with what we've seen. So numerical simulations of galaxy evolution, where galaxies have misaligned components, they see an increased inflow of gas to the center of the galaxy. So in numerical simulations, we don't actually see the gas falling onto the black hole because we don't have the resolution. But combined with our observational results, it means that this inflow of the gas to the center actually manages to fuel the black hole. And the reason why this happens is through different dynamical mechanisms, so gas dissipation, stellar torques, and shocks between aligned and misaligned components. So it seems that when we have these misaligned components in galaxies, we have the two ingredients that we need to fuel black holes. We have the gas supply coming from the outside, and we have the mechanisms, dynamical mechanisms, to drive the gas to the black hole. So this is likely an important mechanism to fuel black holes. So now let me tell you a little bit about the properties of the AGN in the galaxies that we observe with this misalignment. So this is looking at how bright they are. So this is work done by a former master student of mine, now PhD student, Martina Winiarska. So she looked at a proxy for the AGN luminosity. So here in the y-axis, this is how luminous the AGN are as a function of the misalignment angle. And this vertical line separates between aligned gas to star rotation and misaligned gas to star rotation. So the first thing that she noticed was that these AGN are not very luminous. So they are low to moderate luminosity AGN. So if you work on the AGN field, it means that they're likely not able to drive strong outflows or affect the gas in the galaxy. And if you look at the purple data points, these are the early type galaxies. What she noticed was that there was no difference in the range of luminosity if we look at early type galaxies with misalignment or early type galaxies with aligned gas and stars. So the conclusion from this, or our hypothesis, is that in early type galaxies, the ones in our sample, the mechanism to fuel the black holes is likely external gas accretion, but it may end up aligned or it may end up misaligned. But our hypothesis is that most of the early type galaxies in our sample are, the black holes in these galaxies are fueled by external gas. Then in our team at Southampton, we also looked at how the gas is distributed. And this is observationally. So we have results from simulations, but we wanted to look at if we look at it as a function of radius in the galaxy, where is the gas? How is it flowing to the center? So this is work that Josep Toos at Southampton is doing. So if you look at in the y-axis the ionized gas surface brightness, so a proxy of how much gas is in the galaxy, as a function of the effective radius in the x-axis. So here, this is closer to the nucleus, this is further away. And he compared the profile of the gas distribution for misaligned galaxies, here in red, and aligned galaxies, so aligned gas and star rotation. So what he found was that galaxies with a large kinematic misalignment have a more concentrated gas profile. So this is in line with these systems facilitating the flow of gas to the center. And this is what we want. We want gas to flow to the center to then fuel the black hole. So it seems that in misaligned galaxies, this is more efficient. And when we put all of this together, and there's some things that I didn't have time to cover in my talk, but we're looking at a type of black hole fueling that is fueling low luminosity AGN. So it's not fueling the brightest quasars. And it's fueling them at a slow rate. So we calculate that this gas inflow and fueling of the black holes will last between 0.1 to 2 gigayears. And this is because the gas is coming from the outside environment of the galaxy. It's losing angular momentum and is slowly flowing to the center. So we don't see peaks of AGN activity, but we see a sustained level of AGN activity at a low luminosity. Okay, so to conclude, I talked about external gas accretion. So this happens when galaxies interact. And in some cases, it can build or replenish the amount of gas that galaxies have. When these interactions result in a kinematic misalignment between stars and gas, we see a higher fraction of active black holes. So there's a connection between these two. And it also results in a more centrally concentrated distribution of gas in these galaxies, which is in line with the inflow of gas to the center as predicted from numerical simulations. So putting this all together, our results show that this is potentially an important mechanism to fuel black holes. is not the only one, right? We know that there are other ways to fuel black holes, but it's very difficult to find mechanisms that observationally and numerically are consistent with being a black hole fueling mechanism. So we think this one is important, and we looked at the low redshift, but we think that if we go to higher redshift, where there are more interactions, then likely this mechanism will play a bigger role there. Okay, I'll stop here. Thank you.
Thank you so much for the very interesting talk. Any questions for Sandra?
What's the mass of this misaligned gas? And I'm wondering for what, how much it dominates the mass of the galaxy or the black hole, how much it might upset the correlation between the two.
We've looked into that. So you're thinking about the increase in mass of the black hole due to this. So to start with the mass of gas, we've calculated, and for early type galaxies is the typical gas mass that they have in the local universe. So between 10 to the 4, 10 to the 6 solar masses for early type galaxies. In terms of the change in the black hole mass, there's been work by Max Baker and collaborators where in numerical simulations, they see that galaxies that spend more time in misalignment configurations, their black holes grow more above the M sigma relation compared to others. So we've tried to look at our sample to see that, but because we have such a small sample, we aren't able to see it yet. But we're trying now to get more black hole masses to see if we can actually see a difference in the M sigma relation. But he predicted that we should be able to see a difference beyond the standard scatter in the relation. So we should be able to observe it if we have a large enough sample.
Could you show your slide right before this one? What do you show? Yeah.
This one, yeah.
Are those 1 sigma error bars?
Yes, yeah.
Then as far as I can see in the central position, that's
Yeah.
a 2 sigma effect.
Yeah, so this is the entire distribution. So the colored regions are the entire distribution, and the error bars are the uncertainty on the mean. Yes, so it is a 2 sigma difference on the mean of the distribution. Yes.
I have a question on the same slide.
Yeah.
So, I'm wondering what the intrinsic mass of the galaxies are. So
Yeah.
the aligned subset presumably may have galaxies which haven't been merged.
Mm-hmm.
So can you compare misaligned galaxies with aligned galaxies of the same mass?
Yeah.
See whether you get the same profile?
Yeah, so we've tried different comparisons, and we always see this difference. So if we compare the same mass range, if we compare the same morphologies, we've done just early type galaxies aligned and misaligned, we still see this difference. So the next step will be to do a one-to-one matched comparison, but it's difficult because of the sample size. But everything that we've tried to separate the sample, we still see a difference.
Thanks for the talk. Can I see the slide before this one?
Yeah.
Oh, thank you. I'm sorry, but is this in infrared or is this in the X-ray?
So the y-axis is optically based estimates of the O3 luminosity. So this is an emission line that is typically used in the optical as a proxy for the total AGN luminosity. Lots of uncertainties there. Our AGN, the way we detect them is via different methods. So optically detected, X-ray, infrared, radio. But here in this plot, you're only seeing the optical luminosity of the AGN.
Yeah, thank you. Because I saw some like a X-ray dim luminosity, but it's also like infrared high because it was obscured by.
Yeah, so we don't have X-ray observations for all of our AGN. It's something that we would like to get. So then we could test if they're obscured or not.
Thank you.
Okay, any final questions for Sandra? Okay, if not, let's thank Sandra again.